Alright, hi guys. This is the part of section 7 that I wasn't able to finish in last night's video, so you'll just start today's class off by watching this real quick. This is called the complex conjugates theorem. So basically what this means is if that I have a complex or imaginary zero, they're always going to come in conjugate pairs. Remember we talked about conjugates when we simplified square roots? And if I had 3 minus the square root of 2, its conjugate was 3 plus the square root of 2. Or if I'm talking about complex numbers, if I have 1 minus I, the conjugate would be 1 plus I. Or if I have 2I, we would say that its conjugate is negative 2I. Okay? So if A and B are real numbers, and B cannot be equal to 0, here I have a complex number, A plus BI. If I know that A plus BI is a 0, or a root of a polynomial function, it cannot happen by itself. So if it's a complex 0, where I definitely have an imaginary part, it cannot come by itself. Its conjugate will always be a 0 as well. So if they tell you 1 plus I is a 0 of a function, you automatically know 1 minus I also has to be a 0 of a function. Just like they have here in the example. If 3 plus 4i is a 0 of this polynomial f of x, then 3 minus 4i also has to be a 0. It's impossible for an imaginary or a complex root that has an imaginary part to happen by itself. They always, always, always happen in pairs. So let's see how we're going to apply this. We're going to apply this when we write polynomial functions. Okay, so we've done this before when they said back in chapter 4, write a quadratic function that has the zeros 2 and negative 5/3, and then you would set up the factors and multiply them out. This is basically the same thing. So we're going to write a polynomial function of least degree with integral coefficients, so that means my coefficients are going to be integers, not fractions or decimals. My zeros have to include 4 and 4 minus I. Now, what they don't tell you here, because you're supposed to know, is that 4 minus I can't just happen by itself. If 4 minus I is a 0, 4 plus I, its conjugate, will also be a 0 every time. Okay, you cannot have a complex 0 that has an imaginary part by itself. They always come in conjugate pairs. So how are we going to set this up? We have to set up our factors. So remember, if 4 is a root, then x minus 4 would be my factor, right? So that's what they have here. X minus 4 is my factor. X minus 4 minus I, notice the parentheses here, and x minus 4 plus I. Remember, that's always our setup. Whatever the root is, x minus that root is the factor. Now, since we're writing a polynomial function, we're going to set it up as f of x equals the product of its factors. So all the factors multiplied together, just like this. And then we have to simplify. So here's our original equation in this part. And what they did to go from the first step to the second step is they said, okay, if I distribute this negative, that gives me x minus 4 and x plus I. So this is x minus 4 plus I. Same thing over here. We distributed the negative. That gave me x minus 4 minus I. And they're noticing that x minus 4 is a term in both of these factors, right? So this is like having something plus I times something minus I. Well, if I multiply those out, that's the difference of two squares. That gives me x minus 4 quantity squared minus I squared. And we know that I squared is negative 1. So what they did to get from the last slide to this slide is they multiplied out x minus 4 quantity squared, which is x squared minus 8x plus 16. And then they replaced I squared with negative 1. So that's how we get to here. Then they simplified. That gives me a 17. 16 minus negative 1. And then we just have to distribute some more. So I multiply this x times everything in my second polynomial factor. And then I multiply negative 4 times everything. And then we simplify by combining like terms. And this would be our final answer. Let me go back here. This would be my polynomial function of least degree. It has integer coefficients, and its zeros would be 4, 4 minus I, and 4 plus I. All right, if you're not sure about the difference of squares thing that we did from here to here, another option that you would have is just to multiply everything out. So you would have from the first row x minus 4 times x minus 4 plus I times x minus 4 minus I. So that's this line right here rewritten. And then you could just distribute. So I would probably multiply out the last two factors first, like this. And then you get this lovely long factor here. And then you start combining like terms. So I only have 1x squared. Then I have negative 8x from combining these two terms. Then notice I have negative ix plus ix, so that cancels out. I have positive 4i minus 4i, that cancels out. Then I have a plus 16 and a minus I squared, which is minus negative 1. And then that gets me back to what we have on the next slide. From here you just simplify and multiply like we did right here. So that would give you your final answer of f of x equals x cubed minus 12x squared plus 49x minus 68. So again, anytime they give you an imaginary or a complex root that has its imaginary part, they always come in conjugate pairs.